It's time to start. And hello, everyone, and welcome to part 3 of PyTorchSim tutorial. My name is Wonhyuk, and I'm from the Parallel System Architecture Lab at Postec. I'm a PhD student there. And in this session, we'll taking a closer look at what's happening inside PyTorchSim. And then we'll do a hands-on exercise where you extend it with a custom instruction. And this is the content, and let's start. Before we dive into PyTorchSim itself, it's important to understand how PyTorch 2 compilation works. When you call torch compile function on a model, two major things happen. And first is graph capture. Torch Dynamo captures your PyTorch model into an FX graph using A10 operations. Second is code generation. Torch Inductor takes that FX graph and turns it into backend specific code. And this is two-stage process. The FX graph is first lowered to a loop level IR. And then the loop level IR is compiled into target machine code. For example, C++ for CPU, Python for GPU, or MLIR for PyTorchSim. To make this more concrete, let's look at a simple example. We have a file called warmup.py, and you can open it Jupyter Lab. And to try it yourself, open a new tab and open a terminal and run below command. And this will let you see Torch Dynamo in action. And I'll give you a minute to try this out and let me know if you run into any issues. Okay, after running warmup.py, you will see the captured FX graph saved as fxgraph.svg and click on it to view the graph. Then you will notice that the graph is expressed in terms of A10 operations. These are the core PyTorch operations that sit at the lowest level of Python API. One important property of FX graph is that it's Python executable and easy to transform. So you can write your own passes to modify or optimize the graph. For more detail, PyTorch's documentation on custom backend is a great reference, and the link is shown below. Now, let's look at what Torch Inductor does with this FX graph. Torch Inductor decomposes and lowers the roughly 1,600 A10 operations down to a smaller set of about 100 loop-level IR operations. This intermediate representation is simpler and hardware agnostic. From this loop-level IR, different backends generate their own target code, C++ for CPU and MLIR for PyTorchSim. And let me give you a quick overview of the key loop-level IR operations. Here, ops.load and ops.store handle tensor memory access through symbolic indices. Then ops.reduction and ops.store reduction perform reductions like sum, max, or argmin. And there's a family of element-wise math operation like ops.add, ops.mer, and ops.absolute, and so on. And these about 100 operations are sufficient to express any A10 operation in a way First, let's look at how decomposition works in torch inductor using the log2 operator as an example. As shown on the right, inductor uses the register decomposition decorator, and this allows us to define log2 using more basic operations. So, it defined using natural log and a multiplication. So once registered, the fx graph is transformed. And you can see that the single log2 node is broken down into two simple A10 operations, log and mer. And in this way, the standard A10 IR is lowered into subset of A10 IR, simplifying the graph. Next, let's examine the code level process of lowering the decomposed A10 IR into loop level IR. Torch inductor executes the fx graph in an interpreter style, traversing each node one by one. And as you can see, when the interpreter encounters a call function node, it accesses a lowering table. And this table, the A10 IR, acts as a key to retrieve its corresponding loop level IR. And these mappings are pre-registered using functions like register pointwise numeric LDF64. And this means that PyTorch already know how each A10 operation should be translated into loop level IR. And furthermore, by updating this lowering table, we can customize the process lowering A10 IR into a different format, such as external library call or predefined template call. And let's walk through a concrete example. Suppose we have a simple add function wrapped with Torch compile. Initially, Torch Dynamo captured this as an fx graph with a single A10 add tensor node. Then Torch inductor lowers this to a pointwise object in the loop level IR. The pointwise type tells us that each element can be computed independently in parallel. And the actual logic is defined in the inner FN. And this inner FN represents the body of the loop that will eventually be generated by the backend. Looking more closely at the computed buffer structure, you can see that it describes the out buffer in terms of device, data type, and size and stride. And in this example, the buffer lives on CPU, holds single precision values, and has a shape of 47 by 10 with row major strides. Finally, let's take a closer look at the internal logic of inner FN. And this is the critical part of the process. Inner FN 0 takes an index as its input. And here, the variable I0 and I1 represent the indices within the predefined range. In the code, you will notice that the memory address is calculated during the ops.load stage. And the index expression calculates the memory address by taking the dot product of indices and strides. And this tells the compiler exactly where to access the data. Once the data is loaded using these addresses, the values are added via ops.add, and then it's returned. And this structure flow allows Torch inductor to precisely map high-level tensor operation. The loop level IR is passed to the CodeGen backend. The primary role of this stage is to map the loop level IR operation into actual code tailored for the target hardware. For instance, as shown in the code snippet on the right, the CPU backend maps ops.apps directly to the C++ standard library function. While Torch Inductor supports C++ and Triton, it is highly extensible. So as you can see on the left, we extend it to support custom backend like PyTorchSim, which generates MLIR. And during this code generation process, optimizations such as tiling, vectorization, and operator fusions are applied to ensure maximum performance. And let's see how the C++ backend handles our add example. The inner fn0 and its metadata on the left are transformed into a single C++ kernel string. And at the bottom of the code, this kernel is invoked with the relevant data pointers. And this is the stage where the actual hardware execution takes place. The ranges 48 by 10 metadata represent a total of 480 iterations. And you can see that this metadata is directly translated into C++ for loop on the right. And the loop iterates up to 480, exactly matching the total elements count. And notably, the loop uses a step of 8 because the backend has applied vectorization, so processing 8 float elements at once in a single iteration. If you look at the highlight sections, you can see that the ops.load and ops.add from the loop level IR have been transformed into vectorized intrinsic functions, such as vectorized float load U. Additionally, the high-level ops.add is mapped to a simple addition, and the return statement is converted into a store operation to write the results back to memory. And this shows how Torch Inductor automatically applies SIMD vectorization to the C++ code, allowing multiple data points to be processed parallelly. Now, for NPU backend like PyTorchSim, we use MLIR, the multi-level intermediate representation. MLIR is an extensible compiler framework designed to address fragmentation across different hardware targets. The key idea is dialects, modular namespace of operation and type that captures different levels of abstraction. For AI accelerator, MLIR is particularly useful because you can define custom dialects for your hardware and write your lowering path to convert high-level MLIR ops down to hardware-specific instructions. And here's a quick example of what MLIR looks like. And this is a simple vector addition. Let's break down. Arith add is a floating point addition operation within the Arith dialect. And it takes two operands, vector A, vector B, then add them together. After that, store the result in C. And the result C is returned as a vector type. As shown here, dialects provide semantic grouping for operation, while the operation itself explicitly defines the operand and result type. And this modular structure allows user to easily customize dialect operation or lowering paths for their specific needs. And PyTorchSim uses several MLIR dialects, which are widely adopted by AI accelerators. For data type, the vector dialect for SIMD vectors and memref for tensor and buffer memory. And for parallelization, the affine dialect, which provides structural loop, constructs, and memory access with symbolic index expression. The arith and math and linear algebra dialects covering arithmetic, math, and math function and linear algebra computation. And this shows how the code generation is performed in PyTorchSim backend. The figure on the right shows the MLIR code transformed from the loop level IR. It consists of a section defining various constants and the main computation loop. And if we take a closer look inside the loop, you can see that IR operations such as ops.load and ops.add have been mapped and converted into affine vector load, arith addf, and affine vector store in MLIR. To understand why the MLIR code look like this, let me briefly describe NPU architecture we are targeting. And the most distinctive feature is related to DMA interface. In this NPU architecture, data movement between the DRAM and the on-chip memory must be explicit. And this means that compiler is responsible for issuing DMA instruction to access external memory. And if you look inside the vector unit, you will notice that each lane has its own independent local scratchpad memory. And this implies that each lane must operate strictly within its own dedicated memory space. And finally, all of these lanes operate simultaneously in a lockstep manner. Because of these architectural constraints, we need to tile the computation. And tiling determines how much data is brought into scratchpad memory and computed at a time. And the constraints are the scratchpad capacity and any operation-specific restriction. And our basic strategy is output tensor tiling using MLIR multi-dim tile class. And the loop structure of kernel looks like this. So load a tile of A and B via DMA, then compute tile. After that, store the result back via DMA. So returning to the MLIR code, we can see how the final output is tailored to our NPU architecture from the loop level IR. And as shown in the example, data movement is handled through explicit DMA operations. And the inner loop is then executed across vector lane in lockstep, with each lane performing operations such as affine vector load, arith addf, and affine vector store in parallel. So in summary, the PyTorchSim CodeGen backend maps loop level IR to NPU targeted MLIR code. And this generate MLIR code then pass through the compiler to be translated into an executable RISC-V binary. Okay, great. And that covers the internals. And now let's move into the hands-on part. So you will working in hands-on notebook. So please open it now and run all cells. So let me show first. So you can use this link. So click this link. And press this button. Like this. Okay. Oh, if you see log like this, then let's move on. And yeah, As you can see in the code, the key function here is torch.exponent2, and it is a A10 IR operator. So once you run all cells, you will see a log output like this. And currently, the exponent2 operation in PyTorchSim is implemented by decomposing it into existing operation. So as you can see, exponent2 is computed by multiplying the input by the natural log of 2 and then applying the standard exponential. And this is functionally correct, but it requires 2 instructions. So our goal is to do better. The goal of this session is to extend PyTorchSim with a custom instruction for exponent2. So here's a big picture of what we are going to do. And currently, A10.exponent2 gets lowered to this MLIR code and then compiled to RISC-V instruction, a multiply, and a custom exponent instruction. So our goal is to replace this with a single custom exponent2 instruction. So the compiler emits just one RISC-V instruction instead of these 2. So to do this, we need to go through 4 steps. Here's the plan. First, we'll define the custom instruction encoding in RISC-V. Then we'll map ops.exponent2 in the loop level IR to an MLIR operation. After that, we'll implement an MLIR lowering path that converts an MLIR operation to the custom instruction. Finally, we'll extend both simulators, Spike and Gen5, to support our new instruction. And let's go through one by one. Okay, RISC-V reserve 4 OP code space, custom 0 through custom 3 for vendors defined extension. And the V6 assigns its instruction to the custom 2 space. And other custom slots can be used for custom instruction, such as DMA instructions. And for our custom exponent2 instruction, we use V6 encoding. And as you can see on the slide, we already set function 6 and VM and function 3 and the OP code to the specific value like this. And this gives us a unique 32-bit encoding that the simulator can decode. And we will use this bit encoding. After that, now it's time to modify the MLIR code generation logic. So we need to implement the exponent2 method so that it emits a mass exponent2. So MLIR operation, sorry. So we have to implement this red box, and the implement looks like this. And this code will emit a single mass exponent2 operation. And so to do this, just click this link to open MLIR OpsPy and go to line 335. So let me show. Open this link and go to line 335. Then you can see the code like this. Oh. So what we need to do is uncomment these lines. So like this. Oh, oops. Like this. And remove these below lines. Yep. And don't forget saving all the changes. Okay, then let's move on to next. Oh, okay, after step 2, let's head back to our notebook to verify the implementation is working correctly. So first, restart the kernel and run cells to ensure a clean execution environment. And next, find the wrapper code path in the output load. Here, like it will be like here. And you can use this path to print out the file. So you can use the cat command to print the contents of the generate wrapper code. Then take a closer look at MLIR output. So you should check whether mass.exponent2 was successfully generated within the inner loop. And let me show first. Yep. Go to notebook. And press this button. Okay, okay. Then after that, copy this line as a wrapper file. Then paste here. Then you can print out the contents of this file. Yeah. For that, run the cells here, and you can see the code like this. Yeah. And try it yourself and make sure that mass exponent 2 appears in your output load like this. And if you have any issues, please raise your hands. Yeah, very good question. So we, that was expected because we haven't yet extended our simulator, functional simulator yet. So we're gonna extend it later. Okay, and let's move on to next. Now, step 3 is to write an MLIR lowering path that converts mass.exponent2 to a V6 operation. And this is the example code. And this is a C++ operation rewrite pattern. So it works by searching for any mass exponent 2 operation in the MLIR code and replacing it with a V6 operation using our defined OP code. So this is a straightforward one-to-one conversion. And there could be more complex cases like memmer, and this would require multi-operation rewrite. But in this case, this is one-to-one conversion, and we have to implement like this. So it's your turn, open this file, test PyTorchSim to V6 conversion.cpp, and go to line 815. Let me show. Open the file and go to 815. I added some guidelines so you can easily find it. Here. So comment out, uncomment these lines. So, like this and like this. Okay. Next. After that, we must register our target operation with the rewrite pattern set. So as shown here, we should add mass exponent 2 v6 function to the patterns. So this tells the compiler to use our specific logic whenever it encounters a mass exponent 2 operation. And also, we need to mark exponent 2 as an illegal operation within the conversion target. So by doing this, we ensure that the compiler's verification stage will flag an error if any exponent 2 operation remain after this lowering process. So just like did within the previous step, so what you need to do is just uncomment these two lines in the source code. So back to the notebook and go to line 935. And here. And uncomment these two lines. Like, sorry. Like this and like this. Okay. Okay. All right. Then move on to next. Now it's time to rebuild the project to apply the changes. So make sure you have saved all the changes. Then first open a new tab in the Jupyter Lab and open a terminal and run the build command shown at the bottom of the slide. So, and it will take about 5 minutes. And if you run into any issues, please raise your hand. So copy the comments from the slide. And open a terminal. Terminal is here, and paste the command like this, and run like this. Oops. Something. Okay. It's working now, and okay, it's done. Is everyone done? Okay. Then move on to next. And once the build is complete, we can verify that the lowering works by running this test. So you can copy this command and paste the terminal and run the command. And then the result will be like this. So let me show. I'll copy the command and execute, run the command. Oh, sorry. And like this. And the result will be like this. There is only one V6 operation. Okay. Move on to next. Now, we need to extend the simulator to support this instruction we define. So let's start with Spike. And it is a functional RISC-V simulator. And to make Spike recognize our new custom instruction, we need to modify some piles. So we need to modify the encoding definition for the instruction we defined earlier. So first, please open first file encoding.h and go to line 28, 23 and uncomment the instruction mask. And let me show. Open the first file and go to 28, 23. Or you can just find the guideline. And you can see it like this, and I'll uncomment these two lines like this and like this. Okay, then scroll down to line 3596. So here, here, 3596, we need to uncomment this line. Like this. Okay, after that, next, move on to next slide. And now we need to implement the Spike custom instruction behavior. So to do this, instead of starting from scratch, we'll use existing file as a template. So first, we simply copy torch.vexponent2.h to a new file called torchsim vexponent2.h using this share command. So copy this command and run this command on the terminal. So copy that, go to the terminal and run the command. Like this. Okay. Now, moving on to next step, and we need to define the actual instruction behavior in Spike. So please click the link to open the file we generated. And if you open the file, you can see the code snippet like this. And there are two nested loops. The auto loops iterates over each vector array, while the inner loop iterates over individual elements within the vector register. And this structure ensures that our operation is applied across the entire vector. And the most important part here is the math function itself. And because we just copy from the exponent to h.h, so here is exponent to f. So we have to change this function, exponent function to exponent to function. So let me show. Open the file and change the exponent to function. Here. So change this like this. And also change this line like this. Okay. Finally, we have two more steps to complete our Spike implementation. And first, we have to open disassembly.cc, and we need to add this assembly entry around line 789. So open the first file and go to line 789. And just uncomment this line like this. Okay, after that, open second file and go to line 136. And let me show. Open the second file. Go 136 up. And change this line like this. So, and this ensures that our new header file is included in the build process. And don't forget saving all the changes. Okay, next. Now it's time to build our Spike. And once again, make sure you have saved all the changes. And this will take about 5 minutes. And copy this command and run the command in the terminal. Sure. Open the open the terminal and run this command like this. Okay. It should look like done. Okay. After the build, And now you can run functional simulation using the functional only configuration. So before running all the cells, please make sure to uncomment the first line as shown here. So set the configuration to functional only configuration. And once you do that, run the cells and check if the output passes the validation against the CPU values. And if you see the passed message, your spike implementation is correct. So let me show first. Go to notebook. Oh. Ah. Go to notebook and set the configuration only mode like this, and restart and run all cells. And the result will be like this. Functionality test passed. And I'll give you some time to finish this build and run this test. And if you run into any issues, please raise your hand. Okay. Now, this is the final step. And for full timing simulation, we also need to support the instruction in Gem5. And to do this, we need to modify these two files. And first, open the first file, decoder.isa, and go to line 4777 and uncomment the lines. So open the first file and go to 4777. Oh, yeah. Here, and change like this. Okay. Okay, then Next, open second file, vector arrays.isa, this file, and go to line 1172. So open second file and go to 1177. Oh, 72. And you can see like this and uncomment these lines. Okay. Okay. After that, we need to update the core CPU files. So first file here, function unit.py, and add custom v exponent 2 to the functional unit list. So open the first file and go to line 124. Open the file and go to line 124. And here, and uncomment this line. Okay. After that, we have to modify second file. So open the second file and go to line 131. And add this line. And yeah, this allows Gem5 to categorize our custom instruction correctly. Okay. Now, after that, this is the final step. We need to configure how this instruction is modeled in the hardware. So open the VPU config py and add custom v exponent 2 to the special function unit list. Since exponent 2 is a complex mathematically operation, we modeled it as an SFU operation. So open the file and go to line 18. Open the file and go to and here. I'll copy this line and paste here, and we exponent 2 like this. Unit change like this. Okay. Now, normally it's time to rebuild Gem5, but to save time with the Docker image we are using already, it includes a pre-built Gem5 binary. So you can skip this build process. And now we've implemented our custom instructions across the entire stack, from the compiler to the simulator, and it's time for the final verification. First, comment out this first line. Then hit the restart and run all cell button. So let me show. Go to notebook. Oh. Yeah. Oh. Oh, yeah, here. And comment out this line and save. After that, I'll press this button. Yep. The result will be like this. Gem5, Spike, and POSIM. Okay. After running the notebook, you will see log like this. And as highlighted in the red box, the PyTorchSim backend successfully triggered 3 different simulations, Gen5, Spike, and TorchSim. And also validation test passed. Now let's look at the result. And the decomposed version is the oldest, and our custom instruction is the newest. You can, you can see the result log by clicking this link, and this is the result. And here we compare the vector unit active cycle between our custom exponent 2 instruction and the decomposed version using exponent plus multiply. With our custom exponent 2 instruction, the active cycle of vector unit are 38. And with the decomposed approach, it takes 30. Can you see the result like this? Okay. Yeah. So throughout this tutorial, we have successfully navigated the entire NPU compiler and simulation stack. So we started by defining custom instruction encoding. Then we implemented MLIR code gen and lowering paths. Also, we extended the Spike and Gen5 to model the functionality and timing of our hardware. So thank you for all your hard work, and feel free to ask anything. Thank you.